Okay, everyone. So we're going to get into I would say, our first major applied math topic. So we're going to be taking the theoretical concepts we've been developing and apply it to situations in science and other applied areas. So the topic is related rates, and and we know that rates basically is another word for derivatives, right? So we're going to be derivatives. We're going to be looking at situations in real world situations where derivatives are related to each other. So for example, here's probably what's the best example of things changing in time. Well, how about the universe, right? So cosmologists say that the universe started with the Big Bang, and then what happened as time? So time here is going this way. What happens as time goes on? The volume of the universe changes. Let's say the density of matter is changing; it's getting less dense. Um, the the radius, so the internal radius is changing. What else? Let's say the energy density, how much energy is in each little bit of space. All of those variables are changing in time, and they're related to each other. So that's an example that would be relevant to this topic. Okay, so we're going to dial it back. Instead of talking about the universe, we're just going to talk about a circle, right? Just a humble circle. So let's say um, A is the area of an expanding circle with radius r. A is the area of an expanding circle with radius r. So let's see here. So we have a circle, and here's the radius. And um, the radius is a function of time, r of t. And so the area, we're going to call that A of t. It's changing too. So first step in this kind of problem is we're going to, what's the connection between these variables? So there's always a connection, a relation between them based on either geometry or physical principles. And in this case, it is just from geometry. Area is pi r squared, right? So we start there. Now, what we do next, we're going to relate the derivative of A to the derivative of r. And what we do is we differentiate both sides. Differentiate both sides with respect to time. With respect to that. So this WRT with respect to time. T. So what do we get? On the left-hand side, what's the derivative of A with respect to time? Well, we just represent that as dA dt. We don't know what it is, but mathematically it's the time derivative. Right-hand side, now we have to be careful. We have to use the chain rule here. So let me write it in two steps. Pi r squared. I usually use square brackets here, don't I? So let me use square brackets. And what is the time derivative? So it'll be, I have to differentiate using the power rule, so it becomes 2r. So let's call it pi times 2r. But then I need the chain rule because r is changing in time also. So it's times dr dt. Let me actually move this circle over a little bit. Everything's cramped here. Speaking of volume expansion, so there we go. Let's move this over. Okay, so times what? Times dr dt. So what I've done is I've treated each variable as a function of time, and therefore I'm actually doing, it looks like implicit differentiation, right? Differentiating both sides. So have I done this? Have I found dA dt in terms of dr dt? Yeah, right? I have the derivative of A expressed in terms of the time derivative. Okay, so these are called related rates. Related rates. So that's why it's called a related rates problem. So what's an example we could use this for? So let's suppose oil is spilling from oil spill from a ruptured ship tanker, and it spreads in a circular area. So um, now it's on the ocean here, right? This is the oil, and it's spreading outwards, right? spreading outwards in time because the oil floats on top of the water. And it's the same as the last situation. So from above, from part A, we know that the rate of change of the area is, I'll call it 2 pi r. I'll just change the pi into 2 pi r times dr dt. So it spreads in a circular area. If the radius is growing at 1 meter per second, how fast is the area increasing when it's 30 meters? So when r equals 30 meters and dr dt equals 1 meter per second, then I can just calculate it, right? The area derivative is 2 pi times 30 times 1 meter per second, which is, I don't know, let's see, 2 times pi times 30. I don't have to do times 1. 188.5, let's call it. And what are the units here? So the units will be meters per second. So that would be meters squared per second. That makes sense because it's area per second, right? So one of the things we can see from this is interesting. So that's our answer. One of the things we can see, though, is that, note, as r gets larger, dA dt also gets larger, even if the radius, even if dr dt is constant at 1. Why is that? Because notice there's this r here, right? So even if the radius derivative, even if the time derivative of r is just 1, let's say the same all the time, as r gets bigger, so that makes dA dt get bigger. So the area is growing faster and faster, even if the radius is growing constantly. Okay, so that's typical for related rates. One variable might be changing in a kind of steady way, but the other one is changing in a slowing down way or an accelerating way. Okay, so we're going to move to a slightly more involved example here. But before that, let's just summarize the steps. So how do you do this kind of thing? So first, draw a picture. It's really important. You have to organize the information. Organize the information that you're given. It's really important to have a pretty clear idea before you go too far into it. So what is the information given? What do you ask for? This is the place where we write an equation. So we write the first equation that relates the variables together. This is a non-calculus equation, like it's just from geometry or from physics or from chemistry. And then we do the calculus part, which is differentiate both sides, and then we should write a sentence as our answer. These are always word problems. So I didn't do that here. Maybe I should actually follow my own advice, right? So I should say the area is then growing at 188.5 meters squared per second. There, so that's my final answer. Okay, so let's carry on with a more involved example, a bit more of a, somewhat more realistic for a test or that kind of thing. So the length of a rectangle is increasing at a rate of 8 centimeters per second, and its width is increasing at 3 centimeters per second. When the length is that and the width is that, how fast is the area of the rectangle increasing? So what's our first step? Draw a picture. Let's try to draw a picture. It's talking about a rectangle. And we have the length and we have the width. So let's call that L and let's call that W. And the area is going to be length times width. So that's our picture. And what are we given? We're given that the length is increasing at 8. So the length, dL dt, is increasing at 8 centimeters per second. And we're given that the width is increasing at 3 centimeters per second. So it's getting longer pretty fast, and it's getting wider not as fast. So those two things together are going to determine how quickly the area is growing. And then we're supposed to we want to do what we want is we want to know we want to know I don't need to write what is. We want to know dA dt when the length is 20 and the width is 10. That's what we want to know. So now we've done the second part. Relate what is given to what is asked for. What's the connection? So the relation is a geometric one here, geometric. And we already wrote it there, right? So that's A equals L times W. And then the next step is we're going to differentiate both sides. Differentiate both sides. So this is like implicit differentiation. So what do? Time derivative. Derivative of A is dA dt. And now on the right-hand side, I'm going to break it up into a couple of steps here. Time derivative of L times W. So what rule do you need here? Product rule. Product rule, which tells us it's going to be derivative of the first, dL dt, times the second, plus the first times the derivative of the second. Okay, so that's my related rates. That's my related rates equation. And now the calculus part is done, and we just need to evaluate. So what do I want to know? I want to know dA dt. Okay, I'm told all these things, right? So dL, I have these four numbers. These are going to go into my expression here. dL dt is 8. W is 10. L is supposed to be 20. And dW dt is 3. So what do I get? That's 80 plus 60 is 140 centimeters squared per second. So we can say final answer. The rectangle's area is increasing at 140 centimeters squared per second. Okay, I said this was close. This is pretty much the same level of difficulty as the previous one, right? So I think we're going to see, let's see here. Here we go. This is a bit more getting to the full scale here, full scale difficulty. Okay, so I think what we're going to do, we've got 6 of those, so I think we'll do one more and then we'll do the rest in another video. Okay, so that makes sense, yep. Maybe 2 more. Okay, so let's read the question and then draw a picture. A plane, an airplane, flying horizontally at an altitude of 1 mile and a speed of 500 miles an hour on a path, this is missing a word, is. A plane is flying horizontally at an altitude of 1, speed of 500 miles per hour on a path directly over a radar station. Find the rate at which the distance from the plane to the station is increasing when it is 2 miles from the station. Okay, well, I've done this problem several times, so I can picture it. Maybe you have to read it again. Don't be afraid to read the question like 3 or 4 times. So what's going on here? So we have the ground, and there's a path. The airplane is flying along this path, let's say. So, and on the ground is a radar station. So maybe that looks like some kind of satellite, some kind of dish. And I don't really know what that means, but so there's a radar station, I guess, is something that tells the plane how far away it is from that point. Okay, so then the plane, let's say, is now I have to try to draw a plane. Let's see here. If you're something of an artist, then maybe you'll like this topic because you can practice your drawing ability. Okay, so there's my airplane flying horizontally. So this altitude, let's do this. This altitude is 1 mile. And it's flying along at 500 miles per hour. Miles per hour. Directly over the radar. So at this moment, it's past the radar tower, but it's on a path that goes over it. Find the rate at which the distance from the plane to the station, let's call that x. That's the distance from the plane to the station. Find the rate at which the distance to the station is increasing when it is 2 miles away from the station. So, actually, let's call this x. Let's call this x because that's more of a horizontal variable, right? Let's call this h for hypotenuse. H for hypotenuse. So let's see, that's our picture, and we're given that the speed, so that would be dx dt. The speed of the plane is dx dt, because how fast that distance is increasing. That's 500 miles per hour. And we're given this, the 1 mile altitude. So let me call this y. So we're given that y is 1 mile. Okay. So I don't think we're given anything else, right? What we want to know is what is the distance, what is the rate at which the distance from the plane to the station is increasing? That would be dh, right? dh dt when it is 2 miles away from the station. So is that when h equals 2 or when x equals 2? So this is a little bit ambiguous, right? Is it when the plane is 2 miles in a horizontal sense or 2 miles in a in the straight line sense? Let me turn off my notifications here. Well, let's assume that it's when h is 2. That's the distance, right? If this was an exam question, you might put up your hand and say, it could be either of these. Which one is it? And then I'd have to tell you. But you can't guess. If a question is ambiguous, you just need clarification. So here I'll just decide this is what we're going to do. Okay, and then what's the relation? So the third step is we need a relation between all these variables. So here it's just Pythagoras, right? Pythagoras. So we could say that x squared plus y squared equals h squared. And I know y, so I'll just put in, y is a constant, so I can just put in the 1. 1 squared is 1. Now, next step, we're going to differentiate both sides. What's the derivative of the left-hand side? 2x times dx dt. Chain rule, right? Plus 0. 2h times dh dt. And now I can evaluate it. I can evaluate my, what do I want to know? I want to know dh dt. So right now I don't, what do I know? I don't know, that's what I want. So I don't know it. H, I will know. I do know that. That's going to be known because it's just 2. dx dt, that is known. That's the speed of the plane. But x is still unknown, right? So let's do that first. How do we find x? So when h equals 2, then x squared plus 1 squared is 2 squared, which means that x squared must be 3, so x is square root of 3, or negative square root of 3. That would be if it's on the other side. If the plane is on the, say, the left side of the tower, then that's also a moment when it's 2 miles away along the hypotenuse. Okay, so now what? So let's evaluate. We'll solve for dh dt. dh dt is 2x dx dt divided by 2h, right? I'm solving for that. So x over h dh dt. And let's put in the numbers. So it's either the cube root of square root of 3 over 2, 500 miles per hour, or the other value of x minus root 3 over 2 times 500. So these are the same in absolute value, just opposite sign. So let's see, square root of 3 divided by 2 times 500, 433.0 miles per hour, or this one will be negative 433. So let's draw a little picture. This is an optional picture, but what's happening here is I have the radar station, and at this moment, here's the airplane. At that moment, it's increasing at the positive value, but if it's over here, because the plane's moving this way, if it's sitting over here, this is also h equals 2. So here, h is increasing at 433 miles per hour. Here, h is decreasing at 433.0 miles per hour. Okay, so final answer. When h equals 2, no, we should go back to real words. When the plane is 2 miles from the radar station, the distance to the station is either increasing, at 433.0 miles per hour if the plane is going away from the tower, is moving away, or it's at negative 433 miles per hour if it's approaching. Done. So we've gone from, it's important with these questions, we go from a word problem, like a verbal description, which is, after all, that's how all the problems in everyday life arise, right? We learn about them in language or in diagrams or conversation. Then we change it into mathematical equations, but then we have to finish up with English again, terms that are understandable to other people who maybe don't know calculus. All right, so we're going to leave that video there and carry on in the next one. All right, see you then.